Hi there, guys. This is the Poisson distribution. This is 13C. Poisson, French for fish. Not sure if that has any relevance here. Maybe it does. So the Poisson distribution is another type of probability distribution, like the binomial distribution, but in this case, there's different parameters and it applies to different situations, of course. After this, we'll deal with the normal distribution as well. So there'll be another probability distribution based in this chapter. So let's give a sort of basic idea of this. Let's come up with an example. So say, for example, I put a meter square grid on a section of grass, and then in that grass we counted the number of daisies in there. Okay, so the number of little flowers that you get in there. Okay, little daisy flowers. Okay, and potentially you could get no daisy flowers, or potentially you could get 100 daisy flowers, or potentially you could get 1 million little flowers cramped into this little space, but it's very, very unlikely that there's going to be these very large numbers. Okay, it might be said that the average is, I don't know, 10, for example. Maybe it's 10 flowers per 1 meter square grid that you put down randomly on a field. Okay, so you could say that X being the number of daisy flowers that you are counting in any one meter grid, would be distributed by a Poisson distribution with a mean of 10. Now, again, there is a formula attached to this, but once again, you don't need to know about this formula. We're going to use this on our GDC. What you need to know is that this is not where you've got a number of trials. There are no number of trials here. We are not necessarily doing this 100 times or 10 times. So this is for any one trial, for any one count. We're talking about there being an average number. And that average number we call lambda. In this case, lambda is 10. That happens also, by the way, to be the expected value. And it also happens to be equal to the variance of X as well. Okay, so remember with the binomial distribution, we had NP was the expected value, and NPQ, Q being the probability of failure, was the variance. In this case, lambda does everything. Okay, so your highest probability in this case would be 10. There would be a bar for 10. This would be the probability scale, and I don't know what that probability would be, but I could find it out. I could do it on my calculator. I could go to Poisson distribution and get the probability of getting a 10 when my expected value, when my lambda is equal to 10 then. So the mean number of daisies is 10. Now, there will be reducing probabilities before 10, and there will be reducing probabilities after 10 as well. And all of these probabilities need to sum to 1. And this will go on to infinity. These are meant to be of size 1, okay? So when you get up to 100, there's going to be very little chance of getting that. When you go up to 1 million, there's going to be even less chance of getting that. But it tends towards infinity here. And this, I don't know what the chance of getting 0 daisies is, but there probably is a reasonable chance of getting 0 daisies there as well. Now, in order for all of this to add up to 1, then the whole thing needs to be scaled, of course. So I don't know what that is. Again, maybe it's 10% there. I'm not really sure. Maybe that's 0.1. I don't know, okay? But we could definitely find that out. We could put it into our calculator if we so desire. Okay, so the height of this would be saying the probability that X is equal to 10 when given lambda is equal to 10 there. When you tell your calculator lambda is equal to 10. Okay, so I've obviously dealt with this in terms of one situation, but what we're really dealing with here are counts of things that happen within a given interval, That could be time or space intervals. So for example, you might be looking at the number of cars that pass your school in a particular hour. Or you might be looking at the number of people in shopping queue that you serve in a shopping queue in a particular hour. Or it could happen, yes, it can happen in time or space. This is a space example here. So these daisies are turning up within space, but randomly so that it's following a mean, that you could potentially have none of these occurrences. You could potentially have infinitely many of these occurrences. The Poisson distribution is also scalable. If I put another grid next to this grid, and I said how many daisies should turn up in 2 meters squared of grass, then I would just scale up my other one. I said, well, okay, well, I'd expect twice as many to turn up. My average would now be 20. Okay, so I would now have a Poisson distribution based on an average of 20 rather than 10. So the thing is scalable as well. Okay, let's see if there's anything else here which I've missed out. So it says an average rate of occurrences in a given time interval is given. Oh, they're calling it alpha. Normally it's called lambda. Same. Okay. In this case, alpha, and is uniform across the time intervals being considered. Yeah, so they turn up, like, for example, cars passing your school, for example, in any given hour. It might be that they turn up, or we assume that they turn up independent of one another. Now, obviously, two cars can't turn up at exactly the same time, and they might be dependent on each other because they might be stuck in traffic. There may be suddenly 5 cars who are all behind each other turning up at the same time. So when you look at that hour-long interval, you might have one here, one here. You might have 5 that suddenly turned up at this point here. And you could say, well, they were dependent on each other because they were stuck in traffic. But for the simplicity of this distribution, we have to assume that all of these things occur independently and randomly within that interval. Okay, because we're modeling real life and we have to make certain assumptions. Okay, and occurrences in a time interval are independent and occurrences cannot occur at the same time or position. That's the assumption. Okay, that's the assumption. Here's the distribution. It's pretty beautiful. E to the minus lambda, lambda to the x over x factorial. Okay, that's the probability that x is equal to any particular outcome that you're interested in. Okay, so for example, if I was interested in putting in x is equal to 10 there, in that previous example, I'd need 10 there, 10 there, and 10 there. Now, of course, the calculator will do all of this for you without you needing to worry about this formula, and it's not given to you in the formula booklet as well, so you don't need to worry about it. Okay, so let's have a look at a question then. So, I just looked this up online for some other examples of Poisson distributions. So this was the number of cases of a disease in different towns. Okay, the number of mutations in any given region of a chromosome, the number of dolphin pod sightings along a flight path through a region, the number of particles emitted by a radioactive source in a given time, the number of births per hour during a given day. I think you get the picture. Okay, so let's look at a question. Let's look at question 8 from 13C, I think, 13C. Let's look at this one here. So question 8, here we go. So it's saying the number of cars breaking down on a motorway is modeled by a Poisson distribution. The average number of breakdowns per kilometer of motorway is less than 1 per kilometer per hour. That seems really high to me. Okay, find the probability that there are no breakdowns on a 5-kilometer length of motorway in 1 hour. Okay, so what we've got here is lambda is equal to the average or expected number per hour. Okay, find the probability that there are no breakdowns. What we want is the probability that x is equal to 0. Oh, I forgot to do this. X is modeled by a Poisson distribution with lambda is equal to 0.597. So we've got probability x is equal to x is equal to 0 here. We can simply put that into our calculator, and I'll just do that live now. So I'm going to go to Scratchpad, and I'm going to go to Menu. I'm going to go to Probability, which is 5 for me on the TI Inspire. And I'm going to go to distributions again. Poisson distribution is, for me, it's Poisson PDF I want. I don't want CDF. I only want one result. So Poisson PDF, lambda is going to be equal to 5. No, it isn't. It's 0.597. And you can see here I'm actually messing up because it's not 0.597, is it? It's 0.597 times by 5. First mistake there, hey. Sorry, this is wrong. That should be times by 5 because it was a 5 kilometer stretch. Okay, so I'm just hoping that I can adapt my calculation here to put in times by 5 into my calculator. And the x value is 0. I'm going to press OK on that one. And I'm getting an answer of 0.0505 to 3 significant figures. Let's just check that one. Check that one. Yeah, we're getting 0.505 there. So they've actually not worked out what the average should be, but they've said 5 times 0.597 there as well. To be honest, you should really calculate that for the examiner. Okay, then it says there are 3 or more breakdowns on a 10-kilometer length of motorway in a day. So I'm missing the question. The question said find the probability that there are 3 or more breakdowns on a 10-kilometer stretch. So we want probability that, let's call it Y this time. Y is Poisson distributed with a Poisson, follows a Poisson distribution rather, times by 10. We can say Y is 3 or more, greater than or equal to 3. So now we're going to use a Poisson CDF in this case. So now we'll do the same thing. So I'm going to go to probability, go to distributions, and I go to Poisson CDF. My lambda is equal to 0.57597 times by 10. The lower bound is 3, and the upper bound is really high. I'm going to put in 5 nines and see how I get on with that. Okay, tab across to OK. Yeah, so you just put in something really large for your upper bound there. It's soon going to tail off to 0. So 0.937 to 3 significant figures, I think. So let's check that one out. I'm messing up again, aren't I? I'm messing up again. You can see I've made a mistake. It said in a day and not in an hour. I'm not reading the question properly. Okay, so actually I needed to do that times by 24. I'm having a good time of it on this one. So times by 24. And so this is wrong. And so it turns out to give you the answer of 1, I believe. Okay, I'm actually going to do this as well. Okay, bear with me. So let's do this. We've got probability, distributions again, Poisson CDF. We've got 0.597. 597, got a lower bound of 3, and we've got an upper bound of all the 9s, and of course lambda is 597 times by 10 and times by 24 in this case. So let's press OK on that one. It doesn't like it. Doesn't like it, so let's do it again. Let's go probability 5. Poisson CDF, we'll go lambda is again, let's try 0.597 times by, what do we have, 240. So lower bound is 3 and upper bound, let's just go with 4 nines. Let's see if it likes that. Yeah, okay, so that's good then. So then it gives us the answer of 1. So obviously that's 1.0000000, or 0.99999999999. So it rounds to 1. Okay. Right. Okay. Let's hope I don't make a mistake on this last one. Apologies for thinking it's so easy that I don't need to pay attention to reading the question. Okay. So 8 part C says there are fewer. Find the probability that there are fewer than 11 breakdowns per day on a 1 kilometer stretch of motorway on at least 5 days of the week. Okay, so what often happens in these questions is they start off as Poisson, and they want you to find a probability that then leads to a binomial distribution probability. Because you can see here they're talking about at least 5 days of the week. So we want to know, we ultimately want to have the probability that X is greater than or equal to 5. And X would be a binomial distribution. It's binomial distribution. There's the chance of this thing happening on 7 different trials, and there's going to be a probability of it happening as well. Now, we need that probability from our Poisson distribution. So I'm just calling these X and Y. You can call them different letters if you want to. If you want to use different letters compared to the previous variables I've used, I'm still going to call this X and Y, and I think we need Y is Poisson distributed, okay, and fewer than 11 breakdowns. So we also need a probability that Y is fewer than 11, so that's less than or equal to 10 breakdowns per day on a 1 kilometer section. So that's following 0.597 on a 1 kilometer section, but it's per day, so that's times 24. And we want to know the probability of getting less than or equal to 10 breakdowns on that one. Less than or equal to 10 breakdowns or fewer than 11 breakdowns per day on a 1 kilometer section. Okay, so we need this probability, and this probability is going to go in there, and then we'll use a binomial probability. So let's get that one out then. So in this case, we have, again, distributions, and we have Poisson CDF, and we have 0.597 multiplied by 24. Lower bound is 0, and upper bound is 10 here. So that's including 10, so this is CDF. So that's getting out the probability of 0.51594, saying everything back to front today, 15494, and so on. Okay, so that's the probability that we get fewer than 11 breakdowns per 24-hour period on a 1 kilometer section of motorway. Now we want that on at least 5 days. So we're putting this probability into here. And we're now going to copy and paste that answer, by the way. So just copy that one. So we're going to go to menu, probability, distributions. Now we want binomial CDF. For me, that's B. So binomial CDF. The number of trials is 7. The probability of success, control paste. Just put it in there. So it's obviously the 0.1549. The lower bound is 5 and the upper bound is 7. I'm pressing OK on this one. My answer that's coming out for this is 0.00143 and so on. Okay, so there we go. Our probability is less than 1%. Let's check the answers in that case. Yeah, okay, so we've got the same answer there. Okay, so same as what we've done there, 24 times the chance of getting a breakdown on one section of the motorway in 1 hour. And okay, so there we go. Obviously, you could base some insurance calculations on this as well if you're giving breakdown cover. Okay, that's good. That's all I'm going to do on this case. I'm not going to go through the example questions that are in the book. They're obviously worked through as well. You can have a look at those ones too. Okay, right. Thanks for listening.